Imagine the universe as a grand, dark stage. Upon it, the actors we can see the blazing stars, the swirling galaxies, the planets, and the nebula perform an intricate ballet. For centuries, we have watched this performance, believing these luminous bodies were the entire cast. We thought we understood the script, written in the familiar language of gravity and light. But now, we are discovering that these actors are not alone. They are being guided, pulled, and shaped by invisible hands. The stage itself is crowded with ghosts. This is the greatest mystery in all of modern science, the case of the missing universe. It is a cosmic detective story, and the prime suspect is an entity we call dark matter. It is not a cloud of ordinary gas that is simply too cold to glow. It is not a swarm of black holes made from familiar atoms. It is something else entirely, a fundamental, invisible component of reality that outnumbers the stuff of you, me, and every star we can see by a factor of 5 to 1. For every ounce of the universe we know and love, there are 5 ounces of this mysterious, unseen substance weaving the fabric of the cosmos itself. The story begins not with a bang, but with a spin. Look at a spiral galaxy, a majestic pinwheel of billions of stars. According to the laws of physics as we know them, this galaxy should be flying apart. The stars at its outer edges are whipping around at such tremendous speeds that the gravitational pull from all the galaxy's visible stars and gas is utterly insufficient to hold them in orbit. It is like a carnival ride spinning so fast that its passengers should be hurled into the darkness, yet they remain securely in their seats. Why? The only plausible answer is that there is more to the ride than we can see. The galaxy is embedded within an enormous, massive halo of something, a gravitational anchor that keeps the stars from escaping. This something is dark matter. The plot thickens when we look at the very largest structures in the cosmos. When we observe immense clusters of galaxies, we see that they possess a gravitational field far stronger than the combined pull of all their thousands of visible galaxies. We can even see the ghost's shadow directly. The mass of these clusters is so great that it warps the fabric of space-time, bending the light from more distant galaxies behind them like a cosmic lens. This effect, called gravitational lensing, creates stretched and distorted arcs of light, the signature of an immense, unseen mass, distorting our view. The light tells us that something huge is there, but our telescopes show us nothing but empty space. What is this ghost? We do not know, and that is the most thrilling and humbling part of this story. We have been able to deduce its existence and map its distribution with remarkable precision, all without ever laying a direct eye upon it. We know it is there because of what it does. It governs the rotation of galaxies. It dictates the architecture of the cosmic web, the vast filamentary structure along which galaxies are strung like pearls on a string. It played a crucial role in the early universe, providing the gravitational seeds that allowed ordinary matter to clump together and form the first stars and galaxies. Without dark matter, our universe would be a dark, formless, and sterile void. There would be no galaxies, no stars, no planets, and no us. Yet, for all its profound influence, it remains utterly elusive. It does not interact with light. It does not emit, absorb, or reflect any form of electromagnetic radiation. It passes through our world, and through us, as if we were not there. Every second, billions of these ghostly particles are streaming through your body, leaving not a trace of their passage. It is the universe's most influential introvert, shaping everything while revealing nothing. This is the heart of the mystery. We are surrounded by the evidence of a cosmic reality that is fundamentally different from our own. We are the fleeting, luminous froth on the surface of a deep, dark, and dominant ocean. The quest to identify dark matter is more than just a technical challenge for physicists. It is a philosophical journey that forces us to question the very nature of reality. What is the universe truly made of? How much of what exists is hidden from our senses? This series is the story of that quest. It is a tale that will take us from the pioneering, overlooked work of a stubborn astronomer in the 1930s to the ultra-sensitive detectors buried deep underground in mines and mountains today, all hunting for a whisper from the dark. It is a story of brilliant deductions, frustrating dead ends, and the relentless human drive to solve the greatest puzzle ever posed. The stage is set, the actors are in motion, and the invisible hands are pulling the strings. The hunt for the universe's ghost is on.
The universe for a long time seemed a place of elegant, predictable order. Since the days of Isaac Newton, we had understood the fundamental dance of gravity. A planet orbiting a star, a moon orbiting a planet. The simple, beautiful rule was that the farther an object is from the gravitational center of its system, the slower it should orbit. This is why Pluto, in the frigid outskirts of our solar system, crawls along its path, while Mercury, close to the sun's fierce embrace, races around at a blistering pace. It was a logic that felt unassailable, a cosmic rhythm that should govern all things, from the smallest asteroid to the grandest of galaxies. When astronomers turned their powerful telescopes towards those grand spirals of stars, like our own Milky Way or its sister Andromeda. They naturally assumed the same rules applied. They pictured these island universes as vast celestial carousels, with stars near the center whizzing around, and those out in the sparse, dark arms moving at a more leisurely, sedate pace. The visible mass, the brilliant core, the sparkling disk of stars, the glowing clouds of gas and dust, was thought to be the entire story. This mass and its resulting gravity was the chain that held the stars in their orbits, preventing them from flying off into the void. This comfortable assumption was about to be shattered by the meticulous, patient work of a scientist who had persistently carved a path for herself in a field dominated by men, Vera Rubin. Armed with a fierce intellect and a deep curiosity about the motions of the cosmos, Rubin found herself drawn to a fundamental question: how exactly do stars in a galaxy move? The theoretical predictions were clear, but hard evidence was surprisingly scarce. Teaming up with instrument maker Kent Ford, whose newly developed, highly sensitive spectrograph could capture the faint light from the outer regions of galaxies, Rubin embarked on a project that would change astronomy forever. She chose the Andromeda Galaxy as her subject. By carefully dissecting its light, she could measure the Doppler shift, the stretching or compressing of light waves from stars as they moved towards or away from us. This allowed her to map the orbital velocities of stars at different distances from the galactic center, from the bright, crowded core to the faint, tenuous edges. She was, in effect, creating a speedometer for the galaxy. What she found was not the gentle, declining curve everyone expected. It was something entirely different and profoundly unsettling. The data points did not fall. Instead, they rose sharply from the center and then leveled off into a flat, unwavering line. The stars at the very outskirts of Andromeda, far from the main concentration of visible mass, were orbiting at nearly the same incredible speed as those close in. The implication was as simple as it was revolutionary. The gravity from all the visible stars and gas was the only force holding the galaxy together. Then these outer stars should have been flung off into the intergalactic darkness long ago. Their velocity was simply too great for the gravitational pull of the seen matter to contain. The galaxy, according to the well-established laws of physics, should be spinning itself apart. Yet it wasn't. It was stable. It had existed for billions of years. Rubin's results, confirmed again and again in galaxy after galaxy, pointed to one inescapable conclusion. There had to be more to a galaxy than meets the eye, far more. The visible stars and gas were merely the tip of a cosmic iceberg. Galaxies must be embedded within enormous, massive halos of something that did not emit, absorb, or reflect light. This something exerted a tremendous gravitational pull, providing the extra force needed to whip the outer stars to such high speeds and hold the entire structure together. This was the first robust, undeniable clue that the universe we see is only a tiny fraction of the universe that exists. Vera Rubin's rotation curves did not just measure the speed of stars. They revealed the gravitational signature of the invisible. The ghost had been sensed not by its own light, but by the way it tugged on the lights we could see. The case of the spinning galaxy was no longer a mystery. It was evidence. The hunt for the missing mass for this dark matter was now the defining quest of modern cosmology, a silent testament to the fact that we are just beginning to understand the true, hidden architecture of the cosmos.
The case of the spinning galaxy, so firmly established by Vera Rubin in the 1970s, felt like a modern revelation. But in the grand detective story of the cosmos, every clue has a precedent. The first shadow of the ghost was cast 4 decades earlier, not in the elegant spiral arms of a nearby galaxy, but in the chaotic, distant swarm of the Coma Cluster. And the man who saw it was perhaps the only astronomer brilliant and combative enough to proclaim it, Fritz Zwicky. Zwicky was a maverick of the highest order, a Swiss-born astrophysicist at Caltech whose intellect was as formidable as his temper. His colleagues often described him with a mixture of awe and exasperation. He was a man who coined the term spherical bastard for those who were bastards no matter which way you looked at them. This was not a man burdened by self-doubt or a desire for diplomatic approval. He saw what others missed, and he had no patience for those who failed to keep up. In the 1930s, the world of cosmology was still in its infancy. Edwin Hubble had recently confirmed that galaxies were the fundamental building blocks of the universe, great island universes receding from one another. Zwicky turned his ferocious attention to one of the densest collections of these islands known, the Coma Cluster, a vast gathering of thousands of galaxies millions of light-years away. Bound together by their mutual gravity, Zwicky's method was as ingenious as it was indirect. He applied the virial theorem, a cornerstone of physics that relates the kinetic energy of a system to its potential gravitational energy. In simpler terms, by measuring how fast the individual galaxies within the cluster were moving, he could calculate the total mass required to keep the cluster gravitationally bound. If the galaxies were moving too fast, the cluster would have flown apart long ago, like a failed explosion. Peering through the 100-inch telescope at Mount Wilson, then the largest in the world, Zwicky painstakingly measured the redshifts of these faint, distant galaxies. The velocities he found were staggering. The galaxies were zipping around at speeds upwards of 1,000 kilometers per second. When he crunched the numbers, the result was shocking. The mass required to hold the Coma Cluster together was hundreds of times greater than the mass that could be accounted for by all the visible stars in all its galaxies combined. It was an absurd result, a number so outlandish it seemed to defy logic. The cluster, by all rights, should not exist. It was a skeleton without enough flesh, a gravitational pit far too deep for the amount of visible matter that filled it. In 1933, in a publication that was largely ignored or dismissed, Zwicky proposed the only explanation that fit the data. There must be additional non-luminous matter present in immense quantities. He called it dunkel materia, dark matter. The scientific community, for the most part, met his crazy idea with a collective shrug. Some questioned his measurements, others his methodology. The discrepancy was so vast, so philosophically unsettling, that it was easier to assume Zwicky, in his characteristic abrasiveness, had simply made a mistake, than to accept that the universe was predominantly made of an invisible substance. The evidence, they argued, was too flimsy, the conclusion too radical. But Zwicky was not a man to be easily silenced. He continued to amass evidence, his eyes seeing the invisible hand at work in other ways. He studied the way light from distant background objects was bent by the gravitational field of galaxy clusters, an early, unheeded hint of gravitational lensing. Everywhere he looked, the story was the same. The cosmos had a hidden, massive component. His voice, however, remained a cry in the wilderness. The world was moving toward war, and cosmology had other priorities. The problem of the missing mass was filed away as a curious, probably erroneous anomaly. Zwicky's reputation as a difficult genius made it easy for the establishment to marginalize his most profound discovery. He was a prophet who saw the ghost in the machine, but few were willing to believe in ghosts. It would take the more careful, systematic, and undeniable work of Vera Rubin a generation later to drag Zwicky's dunkel materiae from the fringes of cosmology into the glaring light of mainstream science. Rubin provided the bulletproof evidence, but Zwicky had fired the first shot. He was the first to sense the vast, unseen architecture of the universe, the first to understand that the glittering galaxies were merely the visible froth on a deep, dark sea of something else entirely. The case of the spinning galaxy, therefore, was not the beginning. It was a confirmation. It was the moment the cold, hard data finally caught up with the brilliant, cantankerous intuition of a man who was decades ahead of his time. Zwicky's crazy idea was, in fact, a stroke of genius, a first glimpse into the profound mystery that would come to define modern physics. The ghost had been named, and though it would return to the shadows for a while, it would not stay hidden for long.
If the mystery of the spinning galaxy was the first clue, and the stubborn galaxy clusters were the second, then the true scale of the conspiracy only becomes clear when we pull back, far back, until entire galaxies shrink to mere pinpricks of light. From this God's eye view, the universe reveals its grandest pattern, its fundamental architecture. It is not a random scattering of stars and galaxies, nor a uniform soup. Instead, we see a cosmic web, a vast, intricate structure of brilliant filaments connecting like threads in a spider's web, immense walls of galaxies and great, dark, empty voids that stretch for hundreds of millions of light-years. This magnificent structure is the single most compelling evidence that we are living in a universe dominated by dark matter. It is a blueprint that could not have been drawn by the hand of ordinary matter alone. To understand why, we must journey back to the very beginning, to a universe that was almost, but not perfectly, smooth. In the fiery aftermath of the Big Bang, the cosmos was a searingly hot, dense plasma of particles and light. Ordinary matter, the protons and electrons that would become everything we see, was constantly buffeted by the intense pressure of radiation. It was like trying to build a structure in a hurricane. Any clump of matter would be blasted apart by the force of light before it could grow. Left to its own devices, the gravitational pull of visible matter was far too weak to overcome this pressure. The universe would have remained a formless, expanding fog, never coalescing into the galaxies and clusters we see today. But there was another component in the primordial mix, a component that felt no pressure from light: dark matter. This mysterious substance, which does not interact with electromagnetic force, was immune to the hurricane. While ordinary matter was being pushed and scattered, dark matter simply sat there, feeling only gravity. And in that nearly smooth early universe, there were tiny, random fluctuations in its density, quantum seeds sown at the dawn of time. Gravity, acting over billions of years, nurtured these seeds. Where there was a slightly denser knot of dark matter, its gravity would pull in more dark matter from the surroundings. Over eons, these knots grew. They became the gravitational anchors, the skeletons upon which the visible universe would be built. They collapsed first into a vast, invisible network of filaments and halos, the scaffolding of the cosmic web. Only then could ordinary matter join the party. As the universe expanded and cooled, the pressure of radiation faded. The atoms of hydrogen and helium, once tossed about, were now free to fall into the deep gravitational wells already carved out by the dark matter. It flowed along the invisible filaments, pooling at the intersections where the dark matter was densest. There, it condensed, cooled, and fragmented, eventually igniting into the first stars and coalescing into the first galaxies. The glittering cities of the cosmos were built upon foundations we cannot see. The evidence for this dark scaffolding is everywhere in the web. The immense voids, the great deserts of space between the filaments, are not truly empty. They contain a sparse sprinkling of galaxies, but they are voids primarily in dark matter. The gravitational pull of the surrounding web has siphoned away both dark and ordinary matter, leaving behind a deep, underdense region. The galaxies we do find in voids are often field galaxies, isolated wanderers that failed to be drawn into the denser clusters. Furthermore, the very shape and dynamics of the web's filaments are dictated by the dark matter. Computer simulations that model the evolution of the universe based only on the known laws of gravity and the presence of cold dark matter have, for decades, predicted the formation of this exact web-like structure. When we compare these simulations to the painstaking three-dimensional maps of millions of galaxies created by powerful telescopes, the match is breathtaking. The simulated universe and the real one share the same cosmic fingerprint. The only way the simulations can replicate reality is by making dark matter the lead actor, with ordinary matter merely following its gravitational script. This cosmic architecture is therefore a fossil record. It is the preserved imprint of the universe's growth, a growth that was guided and accelerated by an invisible framework. The luminous galaxies we survey are like lights strung along invisible cables, tracing a shape that was predetermined long before the first star ever shone. The cosmic web, in its sublime complexity and scale, is the ultimate proof of dark matter's dominion. It shows us that the ghost is not merely a local phenomenon hiding within individual galaxies. It is the master architect of the entire cosmos. It built the stage, drew the blueprints, and directed the flow of the material that would become us. To gaze upon the web is to see the shadow of dark matter cast across the entirety of the observable universe, a silent, hidden presence holding the glittering lights of creation in its embrace.
It is one of the most violent events in the universe, a cosmic collision on an almost unimaginable scale. Some 3.8 billion light-years away, two vast galaxy clusters, each containing hundreds of galaxies, slammed into one another at a speed of millions of miles per hour. Astronomers call this system the bullet cluster, for the distinct bullet-shaped cloud of superheated gas that gives it its name. But this cataclysm is more than just a spectacle. It is a cosmic crime scene, and the evidence it provides has been called a smoking gun in the case for dark matter. To understand what happened here, we must consider the different components that make up a galaxy cluster. First, there are the galaxies themselves, vast collections of stars, each separated by immense stretches of empty space. Then there is the intra-cluster medium, a seething multi-million-degree ocean of thin, ionized gas that fills the space between the galaxies. This gas is the bulk of the normal, or baryonic matter in the cluster. And finally, according to theory, there is the massive halo of dark matter, which provides the cluster's gravitational backbone. When the two clusters of the bullet cluster plowed into one another, a remarkable thing occurred. The different components of the clusters behaved in dramatically different ways, and in their separation they revealed their true nature. Think of it like this. During the collision, the galaxies, with their vast empty spaces, were like swarms of bees passing through another swarm. The chances of two stars actually colliding are infinitesimally small. The galaxies, for the most part, sailed right past one another, largely unaffected by the crash. The intra-cluster gas, however, is a different story. This gas is made of ordinary particles that do interact with one another electromagnetically. It is a tangible, viscous medium. When the two clouds of gas met, they did not pass through each other. They slammed together with tremendous force, like two giant clouds of smoke colliding. The impact created immense shock waves, compressing and heating the gas to even more extreme temperatures, forming the distinctive bullet shape. This gas was slowed down and stuck in the middle of the collision zone. But what of the dark matter? By its very definition, dark matter does not interact with itself or with normal matter through any force except gravity. It is effectively invisible and frictionless. So, when the two halos of dark matter from the colliding clusters met, they should have simply passed through one another, unaffected by the messy gas collision. Just like the galaxies did, this is precisely what the evidence shows. Using an ingenious combination of observations, astronomers were able to map the crime scene. The hot X-ray emitting gas was mapped by NASA's Chandra X-ray Observatory, revealing its location stuck in the center. But the total mass of the cluster, the source of its gravity, was mapped using the phenomenon of gravitational lensing. By measuring how the cluster's gravity warps the light from more distant galaxies behind it, astronomers can create a precise map of where the mass actually is. The result was stunning and unequivocal. The gravitational lensing maps revealed that the vast majority of the mass of the bullet cluster is not in the location of the hot gas. It is not in the middle where the cosmic train wreck occurred. Instead, the mass has sailed ahead, coinciding perfectly with the locations of the galaxies that passed through almost unscathed. The interpretation is inescapable. The mass that comprises the bulk of the clusters, the dark matter, behaved exactly as predicted. It felt no friction, felt no pressure, and simply continued on its trajectory, separated from the ordinary matter that got stuck in the violent collision. This is the smoking gun. The bullet cluster provides direct, visual proof that most of the matter in the universe is not the hot gas or the shining stars. It is something that can be weighed through its gravity, but does not interact with light or with itself. It proves that dark matter is not simply a modification of the laws of gravity. If that were the case, the gravitational lensing signal would have remained centered on the visible gas, where most of the normal matter resides. But it didn't. The gravity had moved. Here, in the aftermath of a cosmic collision, we see the ghost separated from the machine. The invisible scaffolding of the universe has been physically pulled apart from the luminous matter it guides. The bullet cluster stands as one of the most powerful and elegant pieces of evidence in all of modern cosmology. It tells us that dark matter is not a mathematical trick, a theoretical figment, or an error in our equations. It is a real physical substance, a silent and unseen form of matter that holds the cosmos together, and which, in this one dramatic instance, we have finally caught in the act.
The evidence is overwhelming. Something is out there, shaping galaxies, weaving the cosmic web, and revealing its presence only through the relentless pull of gravity. We have named this ghost dark matter. But a name is not an explanation. To understand what it might be, we must first rule out what it is not. The most intuitive suspects, the dark, bulky objects made of ordinary matter that we simply can't see, have been brought in for questioning. And one by one, the evidence has let them go. The first and most natural suspect is what astronomers call massive compact halo objects, or MACOs. This category includes a host of faint but familiar celestial bodies, rogue planets that float untethered to any star, brown dwarfs that never gathered enough mass to ignite, neutron stars, and stellar mass black holes. These are all objects made of protons, neutrons, and electrons, the same stuff as you and me, but which emit little or no light. Could a vast population of these dark celestial bodies be hiding in the halos of galaxies, providing the missing mass? For a time, this was a compelling idea. In the 1990s, several teams set out to hunt for MACOs using a clever technique called gravitational microlensing. The principle is simple. If a massive, compact object passes directly between us and a distant star, its gravity will act as a lens, briefly focusing the star's light and causing it to flare in brightness. By monitoring millions of stars in nearby galaxies like the Large Magellanic Cloud, astronomers could count these telltale flashes and estimate how many MACOs populate the galactic halo. The results were definitive. While a few such events were detected, they were nowhere near enough to account for the immense gravitational pull we measure. MACOs exist, but they are a negligible fraction of the dark matter. The ghost is not a swarm of failed stars and orphaned planets. Perhaps then the culprit is even more exotic, yet still made of ordinary matter. What about vast clouds of cold, dark gas or immense banks of cosmic dust? Could these be obscuring enough mass to solve the mystery? Again, the answer is a firm no. While cold gas and dust do exist, we have powerful ways to detect them. Cold hydrogen gas emits a faint but specific radio signature at a wavelength of 21 centimeters that our telescopes can pick up. Furthermore, any significant cloud of dust would reveal itself by blocking the light from stars and galaxies behind it, or by being heated up and re-emitting light in the infrared. When we add up all the normal, or baryonic, matter that we can detect through all our methods, from the brilliant stars to the faintest wisps of gas, it accounts for less than 1/5 of the total matter the universe is known to contain. The rest, the overwhelming majority, must be something that is not made of protons, neutrons, and electrons. It is not any form of matter we have ever touched or seen. This realization leads to a more radical line of questioning. Could the dark matter be made of black holes after all, but of a more ancient, primordial kind? Theorists have proposed that in the searing heat of the very early universe, random fluctuations could have compressed pockets of space into tiny, incredibly dense black holes, formed not from dying stars but from the raw energy of the Big Bang itself. These primordial black holes, PBHs, some perhaps no more massive than an asteroid, could, in vast numbers, constitute the dark matter. However, this suspect also faces a battery of tough tests. The same microlensing surveys that ruled out MACOs also place severe limits on PBHs. If they were common, we would see far more of those brief stellar brightenings than we do. Furthermore, the precise way in which the cosmic microwave background, the afterglow of the Big Bang, is patterned tells us how matter was clumping in the early universe. The presence of large numbers of black holes would have altered this pattern in ways we do not observe. While a small population of primordial black holes might still exist, they cannot be the main component of the dark matter. So the board is cleared. The ghost is not planets, not dead stars, not gas, not dust, and not ancient black holes made of regular atoms. It is none of the things we know. By process of elimination, we are driven to a conclusion that is as thrilling as it is humbling. Dark matter must be something new. It is an exotic, undiscovered form of matter that does not fit within the standard model of particle physics. It is likely a sea of as-yet undetected fundamental particles. Born in the furnace of the Big Bang, these particles would be electrically neutral, stable over cosmic timescales, and cold, meaning they moved slowly in the early universe, allowing them to clump and form the gravitational scaffolding we observe. They interact with the world of light and atoms so feebly that billions of them pass through our bodies every second without a trace. By ruling out the familiar, we have cornered the ghost into the realm of the fundamentally new. The hunt is no longer for a hidden astronomical object, but for a particle that will redefine the very meaning of matter. The case has moved from the cosmic scale down to the subatomic, and the pursuit is now underway in the deepest laboratories on Earth.
For decades, the case for dark matter has been built from the top down. We have seen its gravitational shadow on galactic rotations, its invisible architecture in the cosmic web, and its ghostly separation from normal matter in cosmic collisions. But to truly solve the mystery, we must shift our perspective. We must move from the cosmic scale to the subatomic, from mapping the ghost's influence to identifying the ghost itself. In the world of particle physics, one candidate has long stood out as the prime suspect: the WIMP, or weakly interacting massive particle. The appeal of the WIMP is rooted in a beautiful, powerful concept known as the WIMP miracle. It's a story that begins not in a distant galaxy, but in the searing heat of the Big Bang itself. In the first fleeting moments of the universe, all of space was filled with a raging firestorm of energy, and every type of fundamental particle that exists. As this primordial soup expanded and cooled, particles and their antimatter counterparts would have annihilated each other in a blaze of radiation. The fate of any hypothetical particle from this era depends on how strongly it interacts with others. This is where the weakly interacting part of the WIMP's name becomes crucial. It does not mean the particles are feeble or unimportant. Instead, it refers specifically to the weak nuclear force, one of the four fundamental forces of nature. This is the force responsible for certain types of radioactive decay. Unlike the electromagnetic force, which affects charged particles like protons and electrons, the weak force is, as its name implies, far less powerful and has an extremely short range. A particle that interacts only via the weak force and gravity would be electrically neutral and would essentially ignore light and normal matter. Now, here comes the miracle. Physicists can calculate what would have happened to a stable, weakly interacting particle born in the early universe. As the cosmos cooled, the frequent particle-antiparticle annihilations would have begun to slow down. For a WIMP, with its specific cross-section, a measure of how likely it is to interact, this freeze-out would have occurred at just the right moment to leave behind a specific relic density of these particles. The astonishing result of this calculation is that the predicted leftover abundance of such WIMPs matches almost perfectly the observed density of dark matter in the universe today. It is a stunning convergence. A number derived from particle physics theory aligns precisely with a number measured by astronomers. This is not a coincidence physicists are willing to ignore. It suggests that the nature of dark matter may be a natural, almost inevitable consequence of the laws of particle physics. So, what would a WIMP be like? Imagine a particle that is, in a sense, a heavier, more reclusive cousin of the neutrino. Neutrinos are also electrically neutral and interact only via the weak force, allowing them to pass through light years of lead without a collision. But neutrinos are famously lightweight and move at nearly the speed of light, making them hot dark matter, which cannot form the fine-scale structures we see. A WIMP, by contrast, is hypothesized to be cold, slow-moving, and massive, perhaps 10 to 1,000 times heavier than a proton. This heft and sluggishness are essential for it to act as the gravitational glue that clumps together to form the scaffolding for galaxies. This theoretical elegance has made WIMPs the reigning champion of dark matter candidates for a generation. It transforms the mystery from an astronomical puzzle into a particle physics experiment. If WIMPs are real, they should be all around us, a vast, unseen ocean left over from the Big Bang. Billions of these massive particles are likely streaming through your body every second, their weak interactions ensuring they leave no trace. This revelation has launched a monumental, decades-long hunt. If WIMPs are here, how do we catch them? Physicists have devised two primary strategies. The first is direct detection, building exquisitely sensitive instruments deep underground, shielded from cosmic rays, to wait for the once-in-a-lifetime event where a WIMP from our galactic halo bumps into the nucleus of an atom, in a crystal or a vat of ultra-pure liquid. The second is indirect detection, using space-based telescopes to scan the heavens for the telltale gamma rays or other particles that might be produced if two WIMPs collided and annihilated each other in dense regions, like the core of our galaxy. For years, hope ran high that a WIMP signal was just around the corner. The candidate was too perfect, the miracle too compelling. The hunt for this prime suspect has driven some of the most sensitive experiments ever built, pushing the frontiers of low background science and engineering. Yet, as of now, the WIMPs have not been caught. The detectors remain silent, and the skies have not revealed the expected annihilations. The prime suspect is proving elusive, forcing physicists to broaden the investigation and consider a wider array of possibilities. The WIMP miracle remains a beautiful idea, but the ghost continues to evade capture.
The reign of the WIMP, as the undisputed prime suspect, has, in recent years, faced a quiet but formidable challenge. While the search for heavy, sluggish particles continues, a radically different candidate has stepped into the spotlight. One that solves the dark matter puzzle, not with brute force, but with ethereal subtlety. His name is the Ixion, and if WIMPs are the hypothetical heavyweights of the particle world, Ixions are its phantoms, ghosts of almost unimaginable lightness, born from a solution to a problem that has nothing to do with dark matter at all. The Ixion's origin story begins not with galactic rotation curves, but with the heart of the atom itself. For decades, physicists have been perplexed by a profound mystery known as the strong CP problem. The CP stands for charge and parity, and the problem is this. The equations of the strong nuclear force, the force that binds quarks together into protons and neutrons and holds atomic nuclei together, allowed for a process that should violate the combination of these two symmetries. This violation would have a dramatic and observable consequence. It would cause the neutron, a fundamental constituent of matter, to possess a measurable electric dipole moment. It would, in a sense, have a slight positive charge on one end and a negative charge on the other. Yet, when physicists measure neutrons with exquisite precision, they find no such thing. The neutron is perfectly symmetric, to an incredible degree. This is deeply puzzling. Why does the strong force appear to respect this symmetry so perfectly when nothing in its fundamental rules seems to demand it? It is as if a powerful law of nature is being obeyed, but no one knows who passed the law. In 1977, physicists Roberto Peccei and Helen Quinn proposed an elegant solution. They suggested that the universe has a new fundamental symmetry that forces the strong CP problem to vanish. Shortly thereafter, Frank Wilczek and Steven Weinberg realized that this mechanism would inevitably produce a new, very light particle. Wilczek named it the Ixion, after a brand of laundry detergent, because it cleaned up a problem. The Ixion, as predicted, would be extraordinarily light, trillions of times lighter than an electron, and potentially billions of times lighter than even a WIMP. It would be electrically neutral and interact with other matter only extremely feebly, primarily through a subtle interplay with electromagnetic fields. But here is the crucial connection to our cosmic mystery. Just like WIMPs, Ixions would have been produced in copious amounts in the hot Big Bang, and because of their unique properties, they would have naturally decoupled as a cold, relic population that permeates all of space. In other words, the same mechanism that solves a deep puzzle in particle physics also produces a perfect candidate for dark matter.
To catch a ghost, you must first build a perfect tomb. The quarry is a whisper, a fleeting tremor so faint that the everyday cacophony of our world drowns it out completely. The most promising signal, the gentle bump of a WIMP against the nucleus of an atom, is so incredibly rare that it could happen to a single atom once in a lifetime. To have any hope of hearing it, you need to listen to billions of atoms at once, and you must do so in the quietest place on Earth. This is the quest that has driven physicists to descend from mountain peaks into the deepest underworld, to laboratories buried so deep that the very rock itself becomes a shield. Our world is constantly bombarded by a hail of cosmic radiation, high-energy particles from distant supernovae and active galaxies. At the surface, these particles create a continuous deafening roar. They zip through our bodies, through our detectors, mimicking the very signal we seek. To have any hope of hearing the faint tick of a dark matter interaction, this cosmic static must be silenced. The solution is to go down deep into the belly of a mountain, where thousands of feet of solid rock act as a vast cosmic umbrella, absorbing the rain of radiation. The journey to one of these laboratories is a descent into another world. Take the Sanford Underground Research Facility in South Dakota, housed in the former Homestake Gold Mine. The elevator ride down is a passage into profound darkness and pressure. You descend for over 10 minutes, past 4,150 feet of ancient rock, to a place where the air is still and the silence is absolute. Here, the overburden shields the lab from nearly all cosmic rays. The only remaining background radiation comes from the natural slight radioactivity of the surrounding rock and the very materials used to build the experiment itself. This is the next frontier of silence. Inside these hallowed halls, the experiments are masterpieces of purity and isolation. They are Russian nesting dolls of shielding, designed to block out every conceivable source of interference. At the heart of these setups often rests a crystal, a vat of ultra-pure liquid or a chamber of noble gas, kept at temperatures near absolute zero. This is the target, the billions of atoms waiting for that 1 in a trillion encounter. But first, it must be protected. The entire apparatus is typically encased in a fortress of lead, mined from ancient Roman shipwrecks that sank to the ocean floor millennia ago. Why such exotic material? Newly mined lead contains a tiny amount of radioactive Pb-210, but lead that has been sitting at the bottom of the sea for 2,000 years has seen this radioactivity decay away, making it incredibly quiet. Around this, there is often a shield of ultra-pure copper and a tank of purified water. The final crucial layer is a veto detector, a surrounding shell of sensitive photomultors that can instantly identify and flag any passing muon or gamma ray from the surrounding rock, ensuring that only the most pristine internal events are considered. The goal is to create an environment so still that the vibration of a truck on a distant highway or the subtle decay of a potassium atom in a researcher's own bloodstream would be a thunderclap. The teams working here become connoisseurs of background, obsessively tracking every possible contaminant. They use radio-pure materials, clean their components in vast ultrasonic baths, and work in clean rooms to prevent the introduction of even a single speck of dust that might carry a radioactive atom. This is the painstaking, unglamorous work of the hunt. For months, sometimes years, the detectors simply listen in the profound dark and cold. The data they collect is a record of almost nothing. And that is the point. Every flicker of energy is scrutinized, its signature analyzed. Is it the telltale single scatter nuclear recoil of a WIMP? Or is it the more complex signal of a known background particle? The tension in the field is palpable. Over the years, a few experiments have seen tantalizing, unexplained excess events, hints of a signal that made hearts race. Dama Libra in Italy, for instance, has reported an annual modulation for over 2 decades, a seasonal wobble that some argued could be the Earth moving through a galactic stream of dark matter. But other larger experiments have failed to confirm it, and the signals remain in a contentious limbo, neither verified nor fully dismissed. The deepest dungeons have so far heard no definitive whisper from the WIMP. The silence is profound, and it is telling. It has begun to rule out vast swathes of the territory where these particles were thought to hide, forcing a re-evaluation of the prime suspect. Yet the hunt does not end. It evolves. The quest for perfect quiet continues, pushing engineers to dig deeper, to purify further, to listen more intently. For in the utter silence of these underground cathedrals, any sound at all would be a revolution. The failure to find a signal is, itself, a crucial piece of data, guiding us away from one ghost and toward the next. In the deepest dungeon, the silence is not empty. It is full of meaning. The hunt for dark matter is a pursuit of the infinitesimal. It demands not just vast underground cathedrals of silence, but also instruments of almost unimaginable sensitivity. In the deepest laboratories, one of the most promising lines of inquiry involves a deceptively simple principle, waiting for an invisible ghost to bump into an atom. The technology designed to feel this bump is a masterpiece of cryogenic engineering, centered on crystals of such purity and cold that they exist on the very edge of motionlessness. This is the world of the crystal trap. The fundamental challenge is one of scale. A WIMP, if it exists, is a cosmic recluse, interacting so feebly with normal matter that it can pass through light years of lead without a collision. To have any hope of catching one, we need to watch a massive number of atoms simultaneously, and we must be able to detect the most minuscule transfer of energy imaginable. This is where the crystals come in. They are not simple table salt crystals, but highly specialized materials like germanium or silicon, or more exotic compounds like sodium iodide or calcium tungstate. They are grown in laboratories with a fanatical attention to purity. For a single radioactive atom embedded within the crystal lattice would shatter the silence with its own decay, creating false signals. But purity is only the first step. The true magic happens when these crystals are cooled to temperatures within a fraction of a degree of absolute zero, 273.15 degrees Celsius. At these cryogenic temperatures, the random thermal jiggling of atoms, the very vibration that defines heat, is almost completely stilled. The crystal enters a state of profound quiet, a near-perfect order where the slightest disturbance can, in theory, be heard. The detection principle relies on a brilliant twofold signal. When a particle, be it a background neutron or just maybe a WIMP, collides with a nucleus within the crystal, it deposits a tiny amount of energy. This energy causes the nucleus to recoil, a microscopic jolt in the frozen lattice. In a conventional detector, this would be the end of the story. But in these ultra-cold crystals, that single tiny jiggle has two distinct measurable consequences. The first is a flash of light. The recoiling nucleus excites the surrounding electrons in the crystal, which then release this energy as a faint pulse of photons. The second is a pulse of heat. The kinetic energy of the recoil is converted into thermal energy, causing an infinitesimal but detectable rise in the temperature of the crystal. This dual signature is the experiment's most powerful tool. By measuring both the light and the heat produced by a single event, physicists can perform a kind of particle forensics, determining the nature of the intruder. This is crucial because the underground silence is not absolute. Background radiation, though minimized, persists. The decay of trace radioactive elements or the impact of residual neutrons can also cause recoils within the crystal. However, these background particles interact primarily with the electrons in the atom, producing a different ratio of light to heat than a WIMP, which is expected to interact almost exclusively with the nucleus. A WIMP collision would produce a lot of heat for a very small amount of light, a nuclear recoil. An electron collision, by contrast, would produce a bright flash of light for the same amount of energy, an electron recoil. By analyzing this light-to-heat ratio for every single event, the crystal trap can effectively sift the potential WIMP signals from the background chatter. The engineering required to measure these signals borders on the miraculous. The crystals themselves are often smaller than a hockey puck, and they are instrumented with sensors that are among the most sensitive in the world. Superconducting transition edge sensors, TES, are glued to the crystal's surface to detect the minuscule heat pulses. These devices operate at the exact razor's edge between their superconducting and normal states, where a tiny change in temperature causes a large, measurable change in electrical resistance. To detect the faint light, another set of ultra-sensitive devices, like superconducting quantum interference devices, squids, or specialized photodiodes, are positioned to catch the fleeting glow. The entire assembly, crystal, sensors, and wiring is then suspended by delicate threads in a dilution refrigerator, a complex apparatus designed to achieve and maintain the millikelvin temperatures required. Any vibration, any stray electromagnetic field, any tiny leak of heat would ruin the experiment. It is a setup of breathtaking fragility designed to detect the most elusive of touches. So far, these crystal traps have heard nothing but silence. They have not yet registered the unambiguous heat and light signature of a WIMP. But this silence is not a failure. It is a process of elimination. With every day the crystals remain undisturbed, they rule out a wider range of possible masses and interaction strengths for the hypothetical particle. They are carving away at the territory where dark matter could be hiding, forcing theorists to consider lighter, fainter, or simply different candidates. In the profound cold and dark, these perfect crystals wait. Their exquisite sensitivity tuned to a frequency of interaction that may or may not exist, listening for a whisper from the ghost that holds the universe together.
While the crystal traps listen in the deep cold for a whisper of heat, another class of experiment has taken a different, equally ambitious path. Instead of small, ultra-pure crystals, these detectors rely on a far more massive and equally pure target: vast, shimmering vats of liquefied noble gases. This is the realm of the Noble Liquid Time Projection Chamber, or TPC, and it represents the scale-up of the dark matter hunt, a shift from an intimate listening post to an industrial-scale observatory. The principle is as elegant as it is complex. Elements like xenon and argon are ideal for this quest. They are noble, meaning they are chemically inert and unlikely to form compounds that could introduce radioactive impurities. When purified to an almost unimaginable degree, they become a pristine, massive target, increasing the odds of that one nitroline interaction with a passing WIMP. A vat containing a ton, or even multiple tons, of liquid xenon presents a vast sea of atomic nuclei for the ghostly matter to bump into. The magic of the TPC lies in its ability to not only detect a collision, but to map it in 3 dimensions. The heart of the detector is a large, cylindrical tank filled with a liquid noble gas, kept at a temperature of around 100 grados bajo cero. At the top and bottom of this tank are arrays of incredibly sensitive light sensors, known as photomultiplier tubes PMTs, positioned both in the liquid and in a thin layer of gas above it. A powerful uniform electric field is maintained throughout the entire volume of the detector. When a particle interacts within the liquid xenon, it does 2 things. First, it produces an immediate, faint flash of light. This is called the S1 signal. The PMTs lining the tank instantly capture this light, telling the scientists that an interaction has occurred and giving them initial measure of its energy. But this is only the beginning. The interaction also knocks electrons loose from the xenon atoms. In a normal liquid, these electrons would simply drift away and be lost. But here, the powerful electric field comes into play. It acts like a gentle, invisible wind, coaxing these freed electrons upward through the dense liquid. After drifting anywhere from a few millimeters to over a meter, they reach the liquid's surface, where the electric field pulls them into the gas phase above. Once in the gas, the electrons experience a much stronger electric field, causing them to accelerate and produce a second, larger flash of light through a process called This is the S2 signal. The PMTs detect this second, brighter pulse of light. This tuple structure is the genius of the TPC. The time between the S1 and S2 signals is crucial. Since the electrons drift at a known, constant speed through the liquid, the delay between the 2 pulses directly reveals the depth of the original interaction within the tank. Meanwhile, the pattern of which PMTs detected the S2 light, which spreads out in a pancake shape at the top of the detector, provides a precise X and Y coordinate. In an instant, the detector has constructed a 3-dimensional map of the collision point. This spatial resolution is a powerful tool in the war against background noise. Radioactive decay from the detector's components or the surrounding environment tends to occur on the outer edges of the tank. A genuine WIMP signal, by contrast, should be uniformly distributed throughout the pristine, central core of the xenon. By focusing only on events that occur in this fiducial volume, scientists can ruthlessly cut away the background chatter. Furthermore, just as with the crystals, the characteristics of the S1 and S2 signals, their relative sizes and timing, can help distinguish a nuclear recoil, a potential WIMP, from an electron recoil caused by a common gamma ray. Experiments like Lux, Xenon, and LZ Lux Zeppelin represent the pinnacle of this technology. Located a mile underground in the Sanford lab, the LZ experiment, for instance, uses a central time projection chamber filled with 10 tons of liquid xenon. It is the quietest, most sensitive place of its kind on Earth, a monument to human ingenuity in the pursuit of the invisible. Every component has been designed for radio purity, from the low radioactivity titanium used in its construction to the continuous purification systems that cycle the xenon, removing any trace contaminants that could mimic a dark matter signal. So far, these magnificent instruments have also returned profound silence. They have probed deeper into the parameter space for WIMPs than any other technology, ruling out vast territories where the particle was once thought to reside. The noble liquid TPCs are not just detectors, they are cartographers of the unknown, meticulously mapping the absences and the silences. They have not yet found the ghost, but they have told us, with ever-increasing certainty, where it is not. And in a mystery as deep as dark matter, knowing where not to look is a monumental step toward finally seeing what is there.
The story of the hunt for dark matter has all the elements of a great mystery. A compelling suspect, brilliant detectives, and ingenious traps set in the deepest dungeons. For decades, the narrative drove forward with the thrilling expectation that a discovery was just around the corner. The WIMP miracle was too elegant to be wrong, the engineering too sophisticated to fail. Yet as the years have turned into decades, a new and profound chapter has been written. One defined not by a shout of "Eureka!" but by a deepening and increasingly significant silence. The world's most sensitive experiments, the crystal traps listening for a jiggle of heat and light, the vast noble liquid time projection chambers waiting for a dual flash in the dark, have, so far, heard nothing. Their data streams, scrutinized by thousands of scientists, remain stubbornly free of the unambiguous signal that would crack the case wide open. The prime suspect, the WIMP, has failed to appear in the lineup. This great cosmic silence is the most important result in modern physics that nobody wanted. The initial reaction to this null result was one of determined refinement. The answer seemed obvious. Our detectors simply aren't sensitive enough. The ghost must be even more elusive than we thought, its interactions even fainter. This belief has fueled an arms race of pure engineering. Each new generation of experiment, bigger, deeper, purer, has been an order of magnitude more sensitive than the last. We have moved from detectors the size of a coffee mug to vats of xenon, weighing multiple tons. We have shielded them with ever purer materials and buried them deeper beneath the earth. We have become masters of quiet, pushing the boundaries of low background science to almost impossible extremes. And yet, the silence persists. This is where the plot truly thickens. The continued non-detection is no longer just a challenge to our engineering. It is a challenge to our imagination. The parameter space where a simple, heavy WIMP could be hiding is being systematically erased. The territory on the theoretical map marked "Here be WIMPs" is shrinking with every passing year, forced into ever smaller and more extreme corners. The great silence is speaking to us, and what it is saying is forcing a profound and necessary crisis in the field. Several possibilities now loom, each more radical than the last. The first is that we are on the very cusp of discovery. The next run of an experiment, the next ton of xenon, the next fraction of a degree in cooling, might be the one that finally breaks the silence. The WIMP is still the prime suspect, and we are merely inches away from finally laying a hand on its shoulder in the dark. The second possibility is that dark matter is simply even more dark than we ever conceived. Perhaps the WIMP's interactions are not just weak, but non-existent for all practical purposes, except through gravity. This would render our direct detection efforts, no matter how sophisticated, fundamentally futile. We would be like deaf men trying to observe a symphony by watching the vibrations on the floor. We can infer the music's power and rhythm, but we will never hear a single note. A third, and deeply unsettling possibility, is that we have been hunting the wrong ghost altogether. The decades-long focus on WIMPs, while productive and well-motivated, may have been a grand red herring. The great silence could be a directive to look elsewhere, to the ultralight, wave-like axions, or to something more exotic still. Hidden sectors of particles, macroscopic blobs of strange matter, or even primordial black holes that have so far evaded our microlensing surveys. This silence is not a vacuum of progress. On the contrary, it is a powerful shaping force. In physics, a null result is still a result. By ruling out vast landscapes of theoretical possibilities, the experiments have performed a monumental act of cosmic cartography. They have drawn a detailed map of the unknown by showing us what is not there. This process of elimination is how science zeroes in on the truth, even when the truth refuses to reveal itself directly. The great cosmic silence is therefore a moment of reckoning and reflection. It humbles us, reminding us that the universe is under no obligation to conform to our most elegant theories. It forces a necessary broadening of the hunt, a creative explosion of new ideas and alternative candidates. The story is not over. It has simply become more complex, more nuanced, and in many ways more interesting than we ever anticipated. The detectives have not failed. The case has just gotten deeper, and in the quiet of the underground labs, the waiting continues, because the only thing more profound than the silence would be the sound of it finally breaking. The great silence from the deepest labs is more than just an absence of data. It is a growing whisper of doubt. For decades, the hunt for dark matter has been guided by a beautifully simple premise: a single, stable, weakly interacting particle left over from the Big Bang. But, as the most sensitive experiments in human history continue to report back with nothing, a radical and thrilling question is moving from the fringes of physics to the center of the conversation. Have we been hunting the wrong ghost? The failure to find a WIMP, despite the compelling WIMP miracle, suggests a profound possibility. Perhaps dark matter is not a single solitary particle living in isolation. What if it is part of an entire hidden cosmos, a dark sector as rich and complex as our own? This idea shatters the minimalist picture and replaces it with something far more strange and wonderful. Just as our visible universe is built from a diverse family of particles, quarks, electrons, neutrinos, all interacting through forces like electromagnetism and the strong and weak nuclear forces, the dark world could have its own ecology. In this paradigm, dark matter would not be one particle, but many. There could be multiple species of dark matter particles with different masses and properties. More startlingly, there could be dark forces that act only within this hidden sector. Just as photons carry the electromagnetic force between charged particles, there could be dark photons, or other dark force carriers, that mediate interactions between dark matter particles. These forces would be completely invisible to us, as our ordinary matter is neutral under them. Just as a neutral atom feels no electric force, this concept of a complex dark sector resolves several nagging issues. For one, it could explain why dark matter forms the specific cuspy halos we observe around galaxies, rather than smearing out into a different shape. The self-interactions within the dark sector, through these dark forces, could allow dark matter particles to cool down and clump more efficiently, just as ordinary atoms can radiate light and collapse to form stars. Some of the small-scale discrepancies between our simulations of dark matter and the actual structures we see in the sky could be neatly solved if dark matter isn't perfectly collisionless but has a subtle ability to interact with itself. This new framework also completely upends the search strategy. If dark matter interacts only through gravity and its own dark forces, then our attempts to detect it via a feeble nudge with an ordinary atomic nucleus were doomed from the start. It would be like trying to detect the presence of a neutrino using only a microphone. They are simply the wrong tools for the job. The ghost is not just quiet. It is speaking a different language entirely, on a frequency our detectors are not built to receive. So how do we hunt for a hidden cosmos? The strategies become more indirect and ingenious. One approach is to look for portals, rare and subtle connections between our world and the dark sector. The hypothetical dark photon, for instance, could have a tiny mixing angle with our ordinary photon. This would create a feeble bridge, allowing energy to occasionally leak from our sector into the dark one, or vice versa. We could search for this by looking for electrons and positrons spontaneously appearing in a vacuum as a dark photon decays, or for missing energy in particle colliders like the Large Hadron Collider, where a collision could produce a particle that immediately vanishes into the dark realm. Another mind-bending possibility is that the dark sector could have its own dark atoms and even dark chemistry. If there are multiple dark particles with opposite dark charges, they could bind together to form complex structures. There could be dark stars, dark planets, and even dark life, all existing in the same space as our own world, yet completely oblivious to us as we are to them. The gravitational shiver we attribute to a simple particle could be the collective pull of an entire, invisible civilization. This is not wild speculation, but a natural extension of the Copernican principle, the idea that there is nothing inherently special about our place in the universe. We once thought Earth was the center of all things. Then we learned the sun was just an ordinary star, and our galaxy merely one among trillions. Now, we are forced to confront the possibility that the matter we are made of is the exotic exception, and that the true vast complexity of the universe is playing out in a dark, parallel reality that shadows our own. The great silence, therefore, is not an end but a beginning. It is the sound of a paradigm cracking, making way for a new and far more expansive vision of reality. The hunt is no longer for a single ghost, but for an entire phantom universe. The detectors may be quiet, but the theoretical landscape is now roaring with possibility. We are no longer just particle hunters. We are cosmic cartographers, trying to map the shores of an invisible ocean that stretches all around us. The case has become infinitely more complex and infinitely more fascinating,